Annenberg Media.
The Grand Canyon, 1.5 kilometers deep and over 300 kilometers long, a gigantic chasm gouged out of the face of the earth by the Colorado River. This is one of the most intricate systems of canyons, gorges, and ravines in the world. The spectacular beauty of this awesome abyss draws millions of visitors each year. But the Grand Canyon is more than just a tourist attraction. It is a stunning microcosm of this planet's geologic history.
The first geologic study of the Grand Canyon was led by geologist John Wesley Powell in 1869. Powell later wrote that the rocks exposed in these canyon walls were an open book of geology. He recognized that the Colorado River had laid open the landscape to reveal one of the most complete rock records anywhere on Earth, one that spans almost 2 billion years of Earth history. To a geologist, a layered sequence of sedimentary rocks like this is a historical record that can be read like a book. As we analyze these rocks from the base of the stack to the top, we're sifting through a wealth of information about the conditions at the Earth's surface at the time the sediments were deposited. Rock characteristics such as mineral composition, grain size and shape, structures within the rock, and even rock color tell us a great deal about the climate, vegetation patterns, position of a shoreline, and the topography of the Earth's surface in the geologic past. The challenge of sedimentary geology is to interpret these clues in the rocks. But in order to do so, we must first understand how sediment is formed and how it's transformed into solid rock.
Sediment is the product of mechanical and chemical weathering and of erosion by wind, water, and ice. Biological activity also plays a role. Sediment may be deposited in the form of sand building up as a dune, or a beach, as pebbles piling up in a stream, or shells and organic matter accumulating on the ocean floor. When a thick pile of sediment accumulates, the particles near the base of the pile are compacted under the overlying deposits. Eventually, they are cemented together to form a solid aggregate rock. Although 95% of the Earth's crust is made up of igneous or metamorphic rocks, the surface itself consists primarily of sedimentary material. The composition of this sediment is controlled by 2 factors: weathering and erosion.
Weathering and erosion influence the composition of sedimentary rocks because, first of all, the mechanical weathering breaks the rocks up in place into smaller pieces, making them more easily eroded. The chemical weathering chemically breaks down certain minerals in preference to others.
One of the most common forms of sediment is referred to as clastic, from the Greek word for broken. Fragments of rocks and minerals falling from an eroding outcrop are examples of clastic sediment. Clastic sediments are classified by size, ranging from large boulders through smaller cobbles and pebbles. Then grains of sand, even smaller grains of silt, and finally, down to the finest sediment of all, clay, which has the consistency of flour. Sediment can be transported in various ways. It can slide down a hillside, be blown by the wind, or be carried along by a flowing stream. As sediment is transported, it tends to be smoothed and rounded as fragments hit and scrape against one another. Sorting is controlled by the size and weight of particles, with the heaviest sediment being deposited first and finer sediment being transported considerable distances.
Deposition typically occurs wherever there's a slowing of the running water. A good example would be at the base of a steep mountain range where the rivers are coming out of a steep canyon into a flat valley. The kinds of materials that would be formed there would be very coarse grain. The further away you get from the front of the mountain range, the finer the grained is the sediment being carried. Consequently, you would get finer grained sandstones or siltstones further away. The same thing happens in an ocean. Where a river enters the ocean, the first things that drop out are the coarser grained materials, generally sand-sized materials. Further out to sea, there will be fine-grained materials. So the sands are usually found on the coasts and shoreline area, where the muds and the clays would be further offshore.
The process which converts loose clastic sediment into solid sedimentary rock is known as lithification, from the Greek lithos, meaning stone.
The first mechanism is one of simple compaction, the weight of the overlying sediment squeezing down grain by grain, causing the grains to ultimately rearrange so that they get into close packing, and finally distortion and perhaps solution of the grains, so that ultimately you have a very tightly packed assemblage of sedimentary grains. At the same time, there may very well be chemical precipitation within the pore space, and that's called, there's two terms that are used here, but the best term for that is cementation. Now, these two processes acting in concert go to make a loose sediment into a hard rock.
In contrast to lithification, sedimentary rocks may also form from the precipitation of chemicals out of water. One common site of chemical sedimentation is desert lakes and lagoons. As evaporation occurs, the chemicals become increasingly concentrated in the water until they can no longer remain dissolved. They combine with one another, forming minerals such as calcite, gypsum, and salt. Deposits formed from evaporation are called evaporites. Chemical sedimentation also takes place in the ocean. Biological processes play a crucial role in triggering this phenomenon. Algae, coral, and invertebrate organisms all utilize calcium carbonate in constructing shells and reefs. When these organisms die, their carbonate hard parts accumulate on the sea floor to form limestone, one of the most common sedimentary rocks on Earth. Limestones vary greatly in appearance, from formations packed with large fossils to beds of chalk formed from the microscopic shells of plants and animals. Life also contributes to the formation of sedimentary rocks other than limestone. In the cool, nutrient-rich water near some continental shelves, radiolaria and diatoms thrive. These suspended microscopic organisms use silica to make their shells. When they die and settle to the sea floor, the silica accumulates to form layers of chert and diatomite. In swampy bayous and deltas onshore, the remains of moss, leaves, roots, and tree trunks may gradually compact over millions of years, giving rise to another sedimentary rock, coal.
Coal is formed as in areas of swamps, quiet water, like Okefenokee Swamp, and areas in the Southeast Asia where you have lots of vegetation in shallow water. Over millions of years, the material grows, dies, settles down due to the chemistry of the water. The material does not rot away. It is preserved. Layer after layer builds up. And with time, sufficient pressure, it's converted first to peat and eventually to coal.
The places where sediment is deposited vary enormously, from glacial valleys, lakes, beaches, river deltas, to the sea floor. These environments of deposition are nearly always initially associated with water, but may eventually transform into dry land.
Geologists interpret the characteristics of sedimentary rocks using the principle of uniformity. This principle is a model of the way sedimentary rocks form. According to this model, we accept that sedimentary rocks have formed throughout geologic time in exactly the same way that sediments are forming today. Throughout Earth history, the same geologic processes, such as weathering, running water, wind, tides, changing sea level, have created and deposited sediments that eventually were hardened into rock. The principle of uniformity says that the present is the key to the past. So as we study sediments being deposited right now and associate their characteristics with the conditions at the Earth's surface, we're creating models for interpreting environments in the geologic past. This principle can be very easy to use. This limestone, for example, is made of gray calcium carbonate mud, a little quartz sand, and the fossils of marine organisms. Sediment being deposited in shallow tropical seas, such as the Bahamas and the Florida Keys, would look very much like this limestone if they were hardened into rock. So in this case, uniformity is telling us that this area was covered by a shallow tropical sea about 250 million years ago. When geologists use the principle of uniformity to analyze an entire sequence of sedimentary rocks, the changing environments recorded in that sequence of rocks shows us how the Earth's surface itself changed and evolved through time.
The deposition of sediment is recorded in the rock record as sedimentary structures.
Sedimentary structures are useful to us because they can allow us to reconstruct the environments of deposition of the sediments. And that's where the sedimentary structures are formed. They're not formed during erosion, they're not formed during transportation, but during deposition. So the sedimentary structures, and there's a very wide variety of sedimentary structures, are indicative of a given site of deposition.
One of the most obvious of these structures is bedding, the layer cake pattern of rock strata. The contact between two layers of rock is called a bedding plane.
One of the very distinctive and probably the most compelling sedimentary structure that one sees when one looks at a stack of sediments is beds. Bedding surfaces represent interruptions. They may be long interruptions or short interruptions. They may be just pulses of sediment where an interruption lasts just a momentary interruption. They may be interruptions of thousands or even millions of years. What is very obvious from everything we know now is that the sedimentary column that we have, the bedding surfaces themselves almost certainly represent far more time than the stack of sediments that we have preserved.
The law of original horizontality states that most bedding initially forms in a horizontal orientation as material settles to a lake bed or the sea floor. But in some cases, sloping layers of sedimentary rock build up. For example, wind can pile up sand as dunes. As mineral grains of diverse color and composition are blown across the dune, discernible layering can develop, inclined at an angle parallel to the slope of the dune. Such angled layers also develop in sandbars and stream deltas. Geologists refer to this as cross-bedding because it cuts across the direction of ordinary horizontal bedding. Sets of cross beds often develop. For example, at any given point in a stream, periods of deposition may alternate with periods of erosion as the velocity of the wind or water changes. A set of crossbeds in a bar will be truncated by erosion, then covered by another set of crossbeds when deposition resumes.
Crossbedding is a sedimentary structure that's very revealing. If we look at a set of crossbeds that are very steep, that are truncated by the next set of crossbeds, then we know that we had a river system or a depositional system that was constantly interrupting itself and shifting around. If we have a smooth progradation of crossbeds, we know there's no interruption and it's just a steady stream of deposition in more or less a constant fashion.
Geologists find crossbeds useful in determining the direction of sediment transport in ancient river and dune systems. Crossbeds form perpendicular to the direction of the water current and tend to slope downstream.
If you've ever looked at a river in any kind of detail, you know that a river tends not to run in a straight line. It meanders around. And so if we get many, many crossbed measurements, then we can come up with a statistical average for the direction the river was flowing. If we go downstream, down that river, we'll find that sorting becomes better, sediment size tends to become less, and so forth.
Another common sedimentary structure, ripple marks, often develops in soft beds of sand lying in shallow water. The to and fro motion of waves creates symmetrical ripples. When they're sculpted by the one-way motion of currents, they are asymmetric, with their steeper sides facing in the downcurrent direction. Sometimes the surface of a fine sedimentary bed is also broken up into a pavement of fossil mud cracks, either with the fissures still open or with the gaps filled in by later deposits of sediment.
Mud cracks are a very good indicator of environments. We've all been in riverbeds or in tidal flats in which we've seen desiccation and the formation of mud cracks. These are preserved in the geologic record. If sand is washed over that mud crack, it infiltrates down into the crack and preserves the crack. We can identify them in river deposits. They show up on natural levees. They show up on floodplains and so forth. They show up in meandering as well as braided streams. They show up in deltaic deposits where a given delta distributary is stranded or abandoned. And so they can be very useful to us because they tell us that the situation at the time of sedimentation was such that it became dry.
By understanding how mud cracks, ripple marks, cross-bedding, and other sedimentary structures and textures form, geologists can, in a sense, read the sedimentary rock record. This allows them to reconstruct the physical appearance of ancient landscapes. One place such work is being done is known as the Ridge Basin, a thick sequence of sedimentary rocks sandwiched between the San Andreas and San Gabriel faults in Southern California. Today, this area is not a basin at all. It is instead part of a young, growing mountain range. Yet 5 to 10 million years ago, it was a deep depression. To determine how the Ridge Basin formed, sedimentologists like Kathy Busby Spera attempt to find out what the Ridge Basin once looked like.
Here we're looking at a very thick succession of fine-grained deposits that we can interpret as lake deposits. There are several lines of evidence that we can use to determine that this was deposited in a lake. First of all, the fine grain size and the thinness of the beds indicates slow deposition by fine-grained sediment settling through a water column. Another thing is that the beds are very laterally continuous, as you can see in this outcrop, which would suggest deposition in a big feature like a lake rather than a small feature like a river channel. The third thing that we can't really see from here is that some of the thinner beds in this succession are limestones, and they bear microfossils that indicate deposition in fresh water. Another feature that we can use to identify a lake is mud cracks and wave ripples. These features all taken together, the wave ripples, the mud cracks, the freshwater fossils, and the fine-grained nature of the deposit, give us real convincing arguments that this is a lake setting.
In places, the edges of the ancient lake can be seen in the rocks. The rivers which once poured into this lake have also left evidence of their previous existence.
This lake was the site of deposition of fine-grained sediments or muds, but periodically rivers built into this lake. What we're looking at here then are the deposits of a river that built out into a lake. This is referred to as a delta. And what we see is a thickening and coarsening upward sequence of beds. The initial deposits of the river are thin to medium bedded sandstones, and these represent sands that jetted out into the lake from the mouth of the river.
The relatively coarse-grained river deposits stand in contrast to the finer-grained, thinly bedded lake deposits. Another sedimentary structure, known as scour and fill, indicates that the velocity of the river fluctuated over time.
Within this sandstone bed, we can see a sedimentary structure referred to as scour and fill. This is a surface running through the rock right here. What we see is that the underlying sandstone has bedding that's truncated by this surface. What this indicates is that flow was so strong during the initial deposition of this sandstone that the current eroded the previously deposited sands. And then, as the current velocity slowed, it began to deposit material. First, it deposited pebbly sands and also deposited these rip-up fragments of mud, and then deposited sand above that. So what we have in this scour and fill surface is evidence, again, of fluctuating current activity within the river channel.
At the margin of the basin, next to the San Gabriel Fault, evidence suggests that the fault was active at the time the basin formed.
We're looking at coarse-grained sedimentary rocks of the basin margin. You can see that the clasts are large and very angular, and that the rocks are very poorly sorted. That is, it's a mixture of all different grain sizes, from sand on up to cobbles. The angularity and the poor sorting indicate that this material has not traveled very far from the source area and was probably shed from the active fault scarp as the basin was downdropped.
Sedimentologists have concluded that this fault activity could itself have created the Ridge Basin. Owing to a bend in the San Gabriel Fault, movement would have stretched the crust in the area of the basin, causing it to sag downward. Through careful fieldwork combining the study of sedimentary rocks with local tectonic history, geologists have reconstructed a detailed view of the ancient Ridge Basin.
Geologists use their understanding of sedimentary rocks to do more than reconstruct the history of the Earth's surface. Most of the economically valuable resources that are extracted from the Earth's crust come from sedimentary rocks. Most people know that sedimentary rocks are the source of fossil fuels, such as oil, natural gas, and coal. But the economic value of sedimentary rocks influences almost every part of our lives. For example, virtually all buildings and public structures require sedimentary rocks in their construction. The cement and the sand and gravel used to make concrete, iron ore for steel, bauxite used in making aluminum, brick and tile, cut stone used for facing large buildings, and even asphalt for the roads which make these buildings accessible. In fact, almost everywhere you look, you can find examples of the commercial and industrial uses of sedimentary rocks.
Though considerably less dramatic than such phenomena as volcanoes or earthquakes, sedimentary rocks are ultimately very important to our modern civilization. Not only can they be economically valuable resources, but in the composition and structure of sedimentary rocks lies the best record of Earth's long and complex history.
To a geologist, this great stack of rocks in the walls of the Grand Canyon contains a fascinating story of Earth history. It's a unique record of changing conditions at the Earth's surface through time, and a storehouse of information about the mountains and the source rocks that provided the sediments themselves. Once we understand the significance of these rocks and of the clues they contain, we can read the record of Earth history like pages in a book in the rocks of the canyon walls. The oldest rocks in the canyon were deposited as sediments about 2 billion years ago. A great pile of sand and mud interbedded with volcanic ash and lava flows filled a rapidly subsiding marine basin. These rocks were deformed in a mountain building episode into an ancient mountain range, the Masatzal Mountains, about 1.5 billion years ago. The mountains were deeply eroded and then covered with a mixture of limestone and shale as sea level rose and flooded the region, creating an unconformity about 1 billion years ago. Mountain building and volcanic activity were then reactivated, followed by yet another rise in sea level and deposition of more marine sediment. In fact, the rocks of the Grand Canyon record no fewer than 4 more repetitive episodes of structural uplift and erosion, followed by deposition of more sediment as sea level encroached on the land and nearby mountains shed sediment into the region. And this process continues today. The Colorado River is now cutting an extraordinary unconformity surface which will eventually be covered with sediments once again. I sometimes wonder what the Grand Canyon will look like when that happens. Will it be covered by an ocean? Will the sediments be shed from mountains yet to be formed? No one yet knows, but one thing is for certain. The answers will be recorded in the sedimentary rocks.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.